Okay, good afternoon, everyone, and thank you for joining me in this presentation. A scalable, high-resolution microchip-integrated liquid metal circuits enabling the next generation of 3R electronics, electronics that are resilient, repairable, and recyclable. So I come from University of Coimbra in Portugal. This is members of my laboratory, soft and printed microelectronics laboratory. We have been funded by national funds from Portugal, including funds that makes us connect us to American universities such as Carnegie Mellon University. And I've been lucky to receive a very generous 3 million euros funding from European Research Council on additive manufacturing of soft electronics and also soft robotics. So my lab is divided to in 4 sections: advanced materials, microfabrications, applications, and also we take into the account sustainability and responsible electronics. So today we want to talk about liquid metals, and specifically we talk about gallium, indium, alloys of gallium, indium, and alloys of gallium, indium, and tin. That this last one, the melting temperature is minus 19 degrees Celsius. And so that's our focus is mostly on stretchable electronics. There are other applications for liquid metals, such as thermal interfacing. There are now applications in cancer treatment. There are applications as radical initiators for polymers and so on. But our applications is mostly on stretchable electronics for health monitoring, wearables, smart textiles, flexible displays, and solar panels. And when we talk about the stretchable electronics, traditionally, there are these conductive composites, there are deterministic structures, and more recently we have liquid metals. There are a lot of conductive composites. They have good performance as long as you stretch them one time, and you don't need to stretch them multiple times. When it comes to multiple stretch cycles, and if you monitor the electrical resistance of these composites, carbon-based or silver-based composites, what you see is that after every strain cycle, you see that the resistance increases and increases until reaching to a point that it's not usable anymore. Whereas liquid metals, they have this very nice characteristic that they remain the same conductivity over thousands, and recently there are data supporting that they can go up to 1 million cycles of a strain, maintaining their basically behavior. So we can say that liquid metals have very high metallic conductivity and fluidic deformability as an advantage. The disadvantage is that they are very difficult to deposit, pattern, and this is very challenging to fabricate circuits with liquid metals. Of course, there has been different works on focusing on liquid metal-based circuits and sensors. Some were microfluidics. Unfortunately, the video, I think, is not working. But we have some microfluidics based that they basically inject the liquid metal into microchannels using a needle. We have solutions based on laser sintering and patterning of nanoparticles made out of liquid metal. And we also have laser patterning, direct laser patterning of liquid metal coats. There are also solutions of printing. There are some attempts to print liquid metal. And although you see that there are basically, you see very nice structure, there are challenges that I will explain in a second. So what happens is that because liquid metal has very low viscosity and is liquid, it's smearing. The adhesion is not good to the substrate. And because of its smearing behavior and this fluidic behavior, is very difficult to make high-resolution circuits. And if you want to put the microchips over that, chances are that your liquid metals start to connect it to each other and make short circuits. So in reality, doing autonomous and scalable fabrication of industry-level high-resolution multilayer circuits that integrate a state-of-the-art SMD microchips has been our focus for the past decade. So we have spent a decade of research on liquid metal-based materials and how to fabricate them, how to deposit them, how to pattern them in order to reach to basically this goal that we have here. And so what today I want to talk about is how we are able to do this kind of circuits based on liquid metal. As you see, we have quite a state-of-the-art microchips integrated into the circuit